middle, then they have to come up and they have to explain what they were doing to the camera.
We were saying we were on lecture 10. Uno.
Oh, gotcha. Right. Yes.
We had a question about the number one that was in the subscript.
Oh, okay. Yeah. Yeah. Okay. So let's maybe do this lecture 10-2. Impedance with two-port elements. So remember, in the preceding lecture, in 10-1, as it were, we yes, 10.2.
No, punto.
Yeah, I'm gonna not say that. I don't know. I don't know what any of these words mean.
Point
Okay.
in Spanish.
Okay.
I see what you're thinking.
Okay, so I don't know enough Spanish to know what's dangerous. No. So, what? I was right?
Well,
There's something close that's...
yes.
Yes. I thought so. See, I don't even need to know a lot of Spanish to know. Yeah. Ooh, okay. See? I'm so good. I'm so good at being so, like, not swearing on camera. I rarely swear on camera. Yes, get the fuck on Slack. Yes. Okay, sorry. So yes, I don't know. It's fun to swear. I like it. I'm not gonna give it up. I'm just not. So we in lecture 10-1 we talked about impedance of one-port elements. So impedance of single elements with just one port on them, like resistors or capacitors or mass elements or fluid inductances or anything like that. So we talked about how to do impedance models for these sorts of elements and how to combine those impedances for networks of connected one-port elements. And now in this lecture, we're going to need to do two-port elements. So remember, two-port elements are those sorts of elements that have two ports. I know the name really gave that away. But also, they're the elements that are energy transducing elements. They convert energy from one form to another, like from electrical to mechanical energy, or from mechanical to thermal energy, or mechanical to fluid energy, or something like that. So these sorts of energy transducing elements will also arise in our systems, and we want to be able to handle them and see what the impedance looks like from one side of the port, from one port to the other, from one side of the element to the other side. And so that's what this lecture is about, 10-2. So the two different types of energy transducing elements that we've considered, transformers and gyrators, reflect or transmit impedance through themselves such that they are felt on the other side. So an example of this is that, for instance, the electrical grid that we have is where the source of the energy is coming from, and then there's a transformer outside your house that transforms that high voltage AC energy into low-ish voltage higher current energy. So that transformer, the impedance of your house gets felt through that transformer. The electrical grid feels it, or you could say the transformer reflects the load of your house to the grid through the transformer. So that's the sort of terminology, the way that we think of this transformer or gyrator relationship. For a transformer, the familiar elemental equations are that the across variable on the side 2 is equal to the across variable on side 1 divided by the transformer ratio, TF, right? And for the through variables, on side 2, we have F2, and on side 1, we have F1, so they're related by this negative TF relationship. So this is familiar to us. Remember that these are the generalized across and through variables. So oh man, that clicking is going to drive me crazy, man. It's a lot of clicking. Thanks. So this, if it was a fluid system on the side 2, this would be P2. And if this was a mechanical, now I've backed myself into a spot here, but I'll say that a mechanical across variable would be V1. So if you wanted to have the pressure and the velocity related through some transformer element, these would be the variables. But these V's are standing in for any across variables that we could be using. So for any type of system, mechanical, electrical, etc. So we're familiar with these elemental equations. This is what we've always been using for these transformers. If we take the Laplace transforms of these two equations, we just have Laplace transform variables V2, V1, F2, and F1. Instead of being functions of time, they're functions of S, the Laplace transform S. Okay? So not too exciting. There's no time derivative involved, so that we don't have to worry about any S terms popping up other than that these are functions of S. Cool. So if on the 2 side, so we're looking at this figure here. On the 2 side, the input impedance is Z3. So we've got everything on the 2 side boils down to this impedance Z3. Could have been a whole network of impedance elements that have been combined to get some equivalent Z3 impedance. This impedance is reflected through or felt on side 1 in a particular way. And that's what we're going to derive here is what is Z1? What is the impedance on side 1 in terms of Z3, the impedance on the other side? So let's go through a little derivation of that. So if on side 2 the impedance is Z3, the equations of 10, 11, which is this line here, these equations, are subject to the continuity and compatibility equations. We could quickly do a compatibility equation here, which would go around in this little loop, which would say that V2, that drop, is equal to this drop, Z3. We could go around the loop if we wanted to, so it would be V2 minus V3 equals 0. In other words, V2 equals V3. For a continuity equation, we could look at this node, or we could draw this contour as we like to do, where we say everything into the contour must equal to everything leaving the contour. So this would be F2 is equal to negative F3, and that's the continuity equation. So there we go. We have our 2 equations. Pretty straightforward. I mean, if this was a circuit, this would be voltage 2 equals voltage 3, and these F's would be current 2 equals negative current 3, right? So cool beans. No, what was the one I came up with? It wasn't cool beans. Awesome possum. Awesome possum. What?
Nothing.
I need to come up with something cooler. Did you call me lame? After all I've done for you? I mean, seriously. I don't know. Substituting these into equation 10, 11, and solving for V1 and F1, we get this. 10, 13. Pretty sure, Anna, I'm pretty sure that you would have bullied me if we were the same age. Like, I would have tried to pretend like I was cool and like it didn't bother me, but it would. It would bother me. I would feel sad inside. I would try to like seem like I was cool and unaffected, but I would be crying on the inside. Yeah. Now I can just pretend better. So V3 and F3 are the across and through variables on side 3, And we can combine equation 10, 12, equations 10, 12, and equations 10, 11 to eliminate the two variables and relate 1 and 3, which is effectively what we're trying to do eventually is relate 1 and 3 here. So that's a good start. So V1 TF V3, F1 is equal to F3 over TF. So we're moving our way. So what we're doing here is we're substituting along. We went from 3 back to 1, and now you kind of have to go the other way again. So you got to kind of go backwards to finally get your solution. The elemental equation for element 3 is V3 equals F3Z3, which can be substituted into the through variable equation to yield. So if we look at our through variable equation right here, we see that F1 is equal to, it's 1 over TF times F3, which is equal to V3 over Z3, right? And working our way back from V3 to V1, we apply the compatibility equation that V2 equals V3 and the elemental equation that V2 equals V1 over TF as follows. So we get F1 equals 1 over TF. V3 is equal to V2, so V2 over Z3. And then we plug in that V2 is equal to V1 over TF. Now we have another TF term that has come in here. So we've got TF squared, and we've got V1 over Z3. Right? Just substituting this into that, and then substituting this into that gives us that. Great. Now, remember the definition of the impedance of side 1 is going to be whatever the across variable is divided by the through variable. That's the definition. So if we finally have an equation that relates these two, which we do, F1 and V1, we solve for V1 over F1, we have the effective input impedance at Z1, which is TF Z3. So that's just solving this equation for V1 over F1. And we get TF squared Z3. So what does this say? It says that the impedance at side 1 of the transformer is equal to the impedance on the other side, so the side that's connected to side 2, but multiplied by the transformer ratio squared. So the transformer affects the impedance with this relationship. It multiplies the impedance on one side by the square of the transformer ratio. So, for instance, if your house was the load here, Z3, then to the grid on the other side of the transformer, your house looks like the transformer ratio squared times the actual impedance of your house. So that's one way to think about it. All right, so remember we have two different types of transducing elements, two-port elements. The one is the transformer that we just covered, and now we also can look at the gyrator, which has gyrator modulus GY, and in the configuration shown in figure 10.3, so this is the way we draw the linear graph for our gyrator model. We have the one side, the two side, we put the Z3 on the two side, and it gets reflected through to the other side in a similar way. So we can do kind of the same derivation where we write down the continuity and compatibility equations. Have you guys done some electronics before?
No, class done any of this is physics.
Yeah, and you guys did like Ohm's law with like resistors and little circuit. Well, we're kind of doing that, but just like super generalized to like all kinds of stuff. So the impedance of this Z3 side over here on the one side of the transducer of the gyrator is the gyrator ratio squared divided by Z3. So it's a different relationship, but it's related, I guess. Similar to the transformer relationship. So this is our impedance on side 1 of Z3. This is how the gyrator reflects the impedance through it. Now let's look at an example, shall we? Okay. So draw a linear graph of the fluid system. So it's actually a mechanical fluid system because we've got this piston cylinder, right? What is the input impedance for an input force to the piston? So we got the schematic. There's a tank of fluid here. We have a piston cylinder that has a force input to it. So the piston, probably we can assume that it's massless because most likely it's going to be a small effect compared to the other forces on this piston. So the piston has force being applied to it. And then on the other side, it's got fluid, and that fluid is being pushed by this piston. Okay, so it puts a force in, it pushes on the fluid. Then there's some restriction here, so maybe like a short pipe or maybe some orifice through which the fluid flows. Often I'll just say water, but it might not be water. It could be some other fluid. Some fluid flows, and it goes into some tank. This tank has got some capacitance associated with it, fluid capacitance associated with it. This is at atmospheric pressure up here. And then it goes through a long, relatively long, thin pipe out to atmosphere. It flows out, so we have a resistance and an inertance or fluid inductance associated with it. So, and out to atmosphere. So this is our system. So let's draw a linear graph model first, shall we? On the mechanical side, let's draw a reference. And on the fluid side, let's draw a reference. The reference on the fluid side is typically going to be atmospheric pressure, and it makes sense to use that here. The reference on the mechanical side could be, for instance, zero velocity. It's fine. It's not. It just needs to be some constant velocity, right? An inertial reference frame. It's the important thing. And then we have a mechanical node, which is going to be the distinct translational velocity of this piston. We're putting in a forcing function to it. We're forcing it with an applied force, Fs. And we could include mass on this as an effect. Let's just assume that this piston has a relatively small mass for the forces that we're looking at here. So we won't put in a mass here, but we will be interacting with the fluid system through this piston, right? So we've got that happening. So this is side 1 of the interaction of this transducing element, energy transducing element. On the fluid side, we're definitely going to have some pressure that's going to be associated with this region here, right? So let's go ahead and put in a node there for that pressure. That's going to interact with side 1. So side 2 we'll call this. This is the transducing element, and this is so this represents the piston cylinder. And then we're going to go through a resistance to, so this is through R1, to this capacitor, right? There's some pressure here.
Bless you.
Wow. I'm gonna lie, I tried to hold it in.
Did it hurt?
No,
Oh, okay. It was just gross.
I didn't force it, but I tried. You know.
Appreciate it. Yeah. Okay, so this goes to a capacitor, which is referencing the atmospheric pressure, right? So it has a capacitance C to atmosphere. And then this pressure is the same along the bottom of this tank. And then we go to R2 here, which is going to go, so we're going to go through R2 and I back out to atmosphere. So R2, let's say, and then the inertance back to atmosphere. So there's our linear graph, this representation. And we are, it's not super important, but we do want to know if this is a gyrator or if this is a transformer. That's like the main question we want to know. We want to know how the impedance of all this stuff gets felt by this source. What is the input impedance for this entire system? So that's our goal. Is we need to know if this is a transformer or a gyrator. We don't really need to know the gyrator modulus, but we generally have an idea of how this is going to go, though, right? So a piston is going to distribute a force across an area, right? With cross-sectional area A, we'll say, of this cylinder. So if it uniformly distributes this pressure across this area, then we're going to have this relationship that the pressure, I'll call this like P, well, it's associated with, it's actually on this side, it's P2, right? So P2 is going to equal, Fs times the area, right? Or no, divided by the area. Force over area, right? So that's the relationship that we have. And then the flow rate and the velocity are related in a similar way. Okay? Now, good. So we've got a through variable on the one side. We've got an across variable on the other side. So what do we have? Is this a transformer or a gyrator? Don't let our guests respond. That would be embarrassing for you guys. I mean, I would be like, ouch. I mean, they just showed up and they know.
It's a gyrator.
It's a gyrator, yeah. Okay, good. You guys aren't embarrassed? I know, you guys didn't have the information to know, actually. But if you guys had guessed it, you did have a 50-50 chance. If you guys had guessed it correctly,
Go with one.
I was gonna make fun of them mercilessly. It's what Anna would do. I try to set the bar high. So it's the bee's knees. Yes. Okay. So a gyrator. So if a gyrator and it has Gy is the gyrator modulus. Gy is equal to -1 over A in the case of a piston cylinder. So, all right, so this is what we've got. Now, if we know that this is a gyrator, we know all of the information that we need to do our analysis of what the impedance is of this entire system felt by this force, okay? So this is the question, like if you walked up to this thing and you were to push on this piston, what are you going to feel? What is the feel of this entire system responding to this pushing on this piston? So as you know, I have an affinity for one-line answers. And this is the same as we did last time. So let's do a one-liner. Let's see what we do. We want to know what Z1 is, right? We want to know what the impedance is that's felt on the one side of this gyrator. We know that since it's a gyrator, this is equal to gy squared over Z3, the impedance of this entire side over here. Okay? Now, I know that because I wrote it here in 1016. Or more accurately, I typed it at one point, and then the screen wrote it. My wish is the screen's command. Sometimes. Not always, unfortunately. So gy squared divided by the impedance of everything here. So we can combine the impedances just like last time. Now we're back to how we did the last problem from lecture 10 uno. I'm afraid to do the point. I don't remember which one it is. Okay. Okay. So Z3 is the impedance of these things combined. So let's just say it's ZR1 in series with this parallel series shit, right? We gotta figure that out. So ZR1 plus the parallel connection here, so that's 1 over ZC plus 1 over, it's the impedance of these two things combined, right, in series. So it's ZR2 plus ZI. That just like got really small for no apparent reason, but I think you guys are tracking. And like we're kind of done, right? I mean that was like the whole thing. I mean we should clarify that ZR1 is equal to what? R1. ZR2 is R2. ZC is? No, it's not. But it was a good guess. Do you guys remember
1 over CS?
1 over CS? So if you guys want to use the table as a little cheat sheet, a fluid capacitor has impedance 1 over CS. And the inertance has impedance IS. Also, fluid inertance, IS is the impedance. IS. Great. So if you go ahead and plug those in, and I did at some point, and I got an answer. So I simplified it down. It isn't that messy to simplify, but it did take a minute. These are old. This one. Aha! There we go. I got 1 over a squared times a large fraction, and the fraction is CI S squared plus CR2 S plus 1. And then in the denominator we have R1 CS squared plus R1 R2 C plus I S plus R1 plus R2. Yeah, it's kind of a big one. And so yeah, that's the input impedance of the entire system as felt by our force source, our input. Okay, so this is the example. So I mean, it was kind of the same as the last example we did, except we had a nice energy transducing element in there, and we learned how to deal with that without having to go through the whole derivation every time, which would suck. But it's fine. Okay, so any questions on that part? Cool beans. All right. What's that from? All right.
Kevin Hart.
Is it what?
Kevin Hart.
Oh, is it? Oh, yeah, that's what I'm thinking of.
Alright, a lot of people use that line.
Yes, also seen on lectures done by Dr. Rico Piccone.
JB
Yeah.
Smooth, another guy that uses it.
Who?
You don't know JB Smooth?
JB Smooth?
Yeah, it's that person.
I mean, it seems like somebody that I should collaborate with, clearly. JB Smooth. I feel like I'm afraid to Google anything you guys tell me to Google. All right.